right, we're going to go ahead and get started. We're just at about 2 after the hour. I want to thank everybody for joining us today. My name is Chris Noddle. I'm one of the co-founders of the OpenAir Collective. I'll give you a little bit of background on that in a second. But what we're going to talk about today, which we're really excited about, has been a long time coming and a lot of work is going into this initiative. We're going to talk about unfracking. And this is both an application and a advocacy or a legislative campaign starting in Colorado that's focused on how we can use biochar in multiple different ways to improve the remediation and plugging of orphan and gas wells, of which we have millions across the country and are a major source of emissions and other environmental problems, which we'll talk about today. This session is being recorded, so anybody who's attending or is RSVP'd will receive a copy of it. It will also be posted to OpenAir's YouTube channel and website as well. So we'll go ahead and get started. Let me go ahead and advance my screen there. Those of you, I know many folks who are tuning in are from the OpenAir community, but for those of you who are hearing about it for the first time, OpenAir is a citizen-led global carbon dioxide removal advocacy network. It's entirely volunteer-driven, and we focus on advancing carbon dioxide removal in a number of different ways, including policy advocacy at the state and national level. We have, I think we're up to 9 different pieces of legislation that our members have introduced in the United States as well as in Europe. And we're founded in New York City 3 years ago, but very quickly started to spread throughout North America and now every continent in which people live. I will go ahead and drop shortly a link to OpenAir's website. Please do join us. Everybody is welcome to learn and participate. One of the things that we do that is sort of a signature, I guess, of our approach is that we develop our own policy. So we have members who come up with ideas for policy. They sometimes form small groups and even write the policy and then get it introduced as legislation. And then we citizen lobby, engage directly with legislators. And something that's relevant to today's discussion, as you'll hear, is what we aim for is what we call viral legislation. So we try to get bills introduced and passed in particular places, but if they're applicable in other places, as is this one that we'll discuss today, is we, through our membership, work to get them adjusted and installed in other places. So some of the bills that we've worked on, our very first bill, which we've now passed in different version as law in 3 different states, has 5 different versions of it. So today's discussion definitely is very much starting in Colorado, but as you'll hear, it has a broad application across the United States and likely other places in the world as well. So unfracking, I'm not going to go into this because you're about to hear from our OpenAir member and our team on what we mean by this. But here we're focused on the enormous environmental and climate challenge of orphan wells. And you'll hear about what those are in detail, but they're abandoned former oil and gas wells that no one currently owns, and they continue to produce methane emissions and all sorts of other nasty stuff that have both global and local negative impacts. And so what we're talking about here is, I know this will be a familiar subject. There are many biochar enthusiasts, I'm sure, tuning in, certainly within the OpenAir community. But here we're talking about how can biochar be used as a way to make those plugs better and potentially play a role in taking carbon out of the carbon cycle. And so biochar is a charcoal-like material that's produced from various different forms of bio waste. And in so doing, it locks carbon in and has other benefits, which you'll hear about. And one of the really great benefits of it is it's in the spectrum of things that can take carbon out of the air. It's one of the cheapest and most ready to go. And that carbon that is removed can be decades, even to centuries or millennia. Some people propose that carbon will be taken out of the air. And according to the recently published State of CDR report, the upper bound on how much carbon could be taken out of the air, removed from the carbon cycle per year from biochar, is upwards of about 7 billion tons a year. So it's not a trivial amount. And again, it's very, very versatile. People are thinking of very creative ways to use biochar. You're going to hear about one of them today as a soil amendment to improve soil health, remediating toxins, adding it to high carbon materials like cement as a supplementary cementitious material, absorbing methane, and of course, storing carbon dioxide. And so I'll introduce right now 2 members of the team who will first hear a little bit about them, and then we'll do a short presentation that is pre-recorded that will play. It's about 10 minutes long that Janice recorded. It's excellent. And then we'll have a discussion with the team here, and then we'll take your questions. So if you do have questions, please do. We're not going to do those live, but do put them in the Q&A panel if you can. That just makes them easier to track, because a lot of things will be happening in the chat. So who you're going to hear from right now is Janice Hollowell. She wouldn't say it herself out of modesty, but she is really the key driver behind this effort, and has just been tirelessly focused on how do we make unfracking a reality in Colorado more broadly. So I'll introduce her in just a moment. And then we have Professor Wei Li, who I'm really excited to have, who joined the team. He's our technical expert. He's a civil engineering and environmental engineering professor at Stony Brook University in New York. He got his PhD from the Massachusetts Institute of Technology. And he's really supplying just an incredible amount of technical expertise around the viability of this application and what kind of tests we need to actually put together to ensure that it actually works in ways that we hope it will. So with that, if I could have Janice and Wei go ahead and turn on your cameras and your mics, and we'll go ahead and get started. So I can just stop sharing my screen. Great. Well, thanks everybody again for joining, and let's go ahead and start. It's always important to note that these ideas don't come from the thin air. They come from people, and you're looking at two people that are really trying to drive this right now. And I want to start with Janice. And I'm wondering, Janice, if you could just quickly tell us a little bit about your background, and then if you could talk to us about what led you to this idea. You can obviously describe it at very high terms. You're about to see a video, but let's hear a little bit about you.
Okay. Hi, everybody. I'm Janice Hallowell. I live on a farm north of Boulder, and I've lived in Colorado all my life. I'm an artist. I never thought I was going to get involved with political stuff or climate stuff. But in 2013, 2 years after we moved out to the country, my daughter came down with leukemia. And the doctors all said, well, it's an environmental thing that causes CML, which is chronic myelogenous leukemia. And I thought, well, that's interesting. What is in our environment that could be causing this? There were no answers. A couple of years later, I learned about it was weird. It was the Greenland ice shelf that really got me going. When it started to melt, I thought, you know what? How am I going to spend the rest of my life? I want to help. So I got involved, and I started showing up at Colorado Oil and Gas Commission meetings where they were talking about plugging orphan wells and how many orphan wells there are in Colorado. And there was all this, environmentalists were saying, yes, they're emitting, and the industry was saying, no, they're not. And at the same time, I read this blog about, well, why don't we plug those orphan wells with biochar? Because it would sequester carbon, it would make for stronger cement, it would be, a really good thing to do. And I thought, why aren't we? So I brought it up to the COGCC, and they sort of said, well, that's interesting, but, they didn't move on it. So I moved on it. I decided to explore it myself. And I started doing research, not primary research, just the research of looking at peer-reviewed papers from people who study it, like Dr. Lee. And I started to see that it was even more valuable than the blog post had originally indicated. And so then I met Chris, and we started to talk about legislation in Colorado. And I wrote a proposal. I gave it to my representative, who decided she wanted to sponsor it. That was Karen McCormick. And she took it on, and we've been working together ever since to get it to become a bill, which it is now. It passed its energy committee last Thursday in Colorado, and now it will go to appropriations and then to the General Assembly floor. Meanwhile, as all this has been going on for the last few years, there's been more and more and more evidence that the kind of leukemia my daughter has is linked to the benzene that comes out of fracking wells. And we are downwind about 6 miles from a bunch of fracking wells. So that's kind of what drives me to do this. But also, I feel like everybody in the world, and especially people who are in the area of fracking, and that's, the Front Range of Colorado is for sure in there, we all need to have less of these chemicals in the air. And one thing we can do right now is start plugging the orphans, which are emitting a lot of toxins. So that's what has been driving it. And now we're waiting for the bill to pass. And Chris and I are starting to move into looking at New Mexico and New York and other states who have a lot of orphan wells. So I'll stop there and we'll pick it up later.
Yeah, well, that's a good preview of what we'll get into detail in your video as well as our discussion. Thanks so much, Janice.
Sure.
And Dr. Lee, yeah, if you could, we'll obviously get into the nature of your research, but if you could just give us a little background on you and how you got connected to the issue of orphan wells.
Sure. Thank you, Chris. Hello, everyone. It is my pleasure to join this webinar. My name is Wei Li. I'm an assistant professor in the Department of Civil Engineering at Stony Brook University in New York. My specialty is in geosystems engineering. And over the year, our lab is really set up to find safe and sustainable solutions for subsurface resources explorations. So over the years, we have worked on federal and industrial projects such as geothermal, CO2 storage, and how to manage earthquakes induced by wastewater injection. And this biochar well plugging idea really caught my eyes because this could be the sustainable solution that we're looking for the fossil fuel industry. At a larger scale, this idea helps reverse the current unhealthy carbon cycle by turning the biomass carbon that is about to go to the atmosphere to char and store it underground like coal. From the perspective of the oil industry, biochar could be a better well plug by absorbing toxic gases, just like the active carbon you use in your refrigerator to get rid of the smell. So, however, but before we get too excited and just go ahead and use it in the field, there's a lot of research we need to conduct to verify its feasibility, such as mechanical behavior, fluidity, and specific surface areas under high pressure to see its effectiveness in plugging wells. And I really look forward to this opportunity to get to study it and make it useful for our future purposes.
Absolutely. Great. And what we'll do is we're obviously going to talk about this application. We're going to talk about the bill as well. And then we're going to really end with a call to action. You know, the way that OpenAir works is that if you're out there and you're in a state that has, whether it's Colorado or elsewhere, and what you hear sounds compelling to you and you want to join or start an effort to advance it in your state as well as federally, which is something we'll get into, we want to be in touch. We want to have you join us and make this a movement. So what we're going to do is I am going to share my screen again and I'm going to play the video. And do me a favor, while I'm doing that, Janice, I'm not going to be able to see the chat. If anyone says they can't hear it, go ahead and just pipe up and tell me, and then we'll fix that. But let's go ahead and start the video. Janice, do you want to give a shout out a little bit to your amazing collaborator on the video? It's really quite, that's my embarrassingly busy desktop. But I know you had some help on this video around the animation.
Yeah, there was a wonderful animator out of University of Colorado at Denver who did all of the animation and just helped smooth it over. Yeah. Great.
So this is about 10 minutes long. And I'm going to play it right now, and it's full of great information. So here it goes.
Unfracking, plugging orphaned wells using biochar. What is unfracking? Unfracking uses technology to plug orphaned wells similar to or the same as current oil and gas well plugging, but adds biocarbon in the form of biochar to sequester carbon in the ground, make a stronger plug, and mitigate the ongoing climate effects of leaking wells. The IPCC has stated that we're not going to survive climate change without significant carbon removal and sequestration. They state that biochar buried in the ground has the potential to remove 2.6 billion tons of CO2 per year. It's important to note that the IPCC does not place biochar in the category of high risk or non-permanence. Unfracking is a safe solution for the world's need to sequester carbon. It's safe because biochar is a solid, and when put into the ground, it won't become carbon dioxide gas again. There are approximately 3.2 million orphan wells in the US that need to be plugged. Many of these leak fugitive toxic gases like methane, CO2, and benzene. And over the next decade, as we identify more orphans and transition to cleaner energy, even more wells will need to be plugged. Here's what's wrong with current well plugging methods. Current methods still use primarily Portland cement, which has a huge carbon footprint of its own, without even taking into account the emissions from the orphan well. Portland cement is known to leak, crack, and break down over time in oil and gas plugging. It's estimated that between 2 and 75% of wells plugged with cement will fail. New York State reports that wells capped with cement often crack so that trapped gas from below blows holes in the cement caps and allows gases to leak. With unfracking, the cement will be more flexible and more durable, preventing cracking. We hope to prove that that includes microannually. Let's review what biochar is. This is a biochar particle under a microscope. Biochar is made from woody biomass feedstocks that would otherwise rot, contributing to the overloaded CO2 cycle in the atmosphere. Whether made from dead trees, rice husks, or pecan shells, feedstocks retain the venous cellular structure from the original plant. The biochar molecule is convoluted and porous and contains numerous surfaces that act like a sponge to soak up and hold many times its weight in toxic chemicals. These are slides of Douglas fir bark, and hybrid poplar. You can see they are slightly different from each other, but they all have this in common. The microscopic compartments will absorb CO2, methane, benzene, heavy metals, and VOCs, and keep them from entering the atmosphere. This is a pyrolysis kiln at Seneca Farms in New York State. Biochar is produced when woody biomass is converted thermally in an oxygen-depleted atmosphere in a kiln like this one. The process is called pyrolysis and takes place at temperatures around 800 degrees Celsius. 3 products are generated in different ratios depending on process design. A carbon-rich solid, which is biochar, a gas called syngas, and a liquid, which is called bio-oil. Biochar, the solid carbon form, can then be put into soil or buried in the ground to take that carbon out of the world's carbon dioxide cycle, preventing the return of carbon in the form of CO2 to the atmosphere. There are hundreds of biochar manufacturers across the US providing us with decentralized scalability. Many of them are investing in large-scale pyrolysis kilns like this, and we believe that collectively, they will increase production as soon as there is demand. Here's how biochar sequesters carbon. If we start with, say, 3 to 5 tons of woody biomass that undergoes pyrolysis, we end up with approximately 1 ton of biochar. 1 ton of biochar can contain as much as 80 to 90% solid carbon, depending on the feedstock. 80 to 90% carbon translates to 1,600 to 1,900 pounds of carbon. That's 1,600 to 1,900 pounds of carbon equals 1.6 to 2.7 tons of CO2 equivalent. If plugged with biochar, Dr. Lee at SUNY Stony Brook estimates that each well can house between 10 and 130 tons of biochar, which equals between 37 and 480 tons of CO2 equivalent. The variation in the estimated storage capacity results from well size, depth, the packing density of biochar in those wells, and amount of biochar additive in the cement plug-in casings. These preliminary numbers indicate that wells plugged with unfracking technology will be carbon neutral at least, and in many cases, carbon negative. So 3.2 million wells across the country could potentially sequester 1.5 billion tons of CO2e. Forever, or at least for 1,000 years. Scientists expect that sealing biochar into orphan wells where there is no erosion will keep the biochar sequestering for more than 1,000 years. In addition to being a better plug, capturing fugitive emissions and other benefits, this longevity of usefulness greatly increases carbon credits. There's more. In addition to the benefit of greenhouse gas reduction that comes with any well plugging, unfracking confers the following benefits, making for multiple wins. Further lowering of greenhouse gases and chemical leaks to air and waterways. Significant carbon sequestration. Lowering the carbon footprint of cement used in plugging. Binding fugitive chemicals, including methane and CO2. Providing a use for dead trees cleared from forests that otherwise will emit CO2 and contribute to forest fires. Creating a stronger, more flexible cement that sequesters carbon. Remediating chemicals from the surrounding soil and fostering a healthy biome. Creating interest, urgency, and new revenue streams, including carbon credits and jobs. Creating incentives to expand the biochar manufacturing industry and get more orphans plugged. Creating a healthy, circular bioeconomy. Orphan wells differ based on geologic formations, the state they're in, the year they were put in, and the company that put them in. This diagram is a generic plugged wellbore with generic features. Currently, well plugging is done with Portland cement for casings and plugs, and oftentimes mud, rocks, sand, or gravel are put in the spaces between plugs. Biochar as an aggregate in cement can be used in all cement plugs. Biochar cement can be used wherever existing casings are replaced. Wherever mud, rocks, sand, or gravel are used as filler, solid biochar can be packed into those spaces instead. A thick cap made of biochar cement with an additional bolus or reservoir of biochar could be designed to make a stronger cap that prevents fugitive gases from blowing through the cap. And biochar can be mixed into the existing surrounding soil along with organic material and cover crops to remediate damaged soil around the well site. A feasibility study with a field pilot portion is needed to confirm scientists' expectations of unfracking and to explore specific detail, collect data, and design a cohesive experiment. The scientists and engineers at Stony Brook can work with the DOE to create and implement a rigorous pilot. The desk portion of the study will feature geomechanical modeling and mathematical calculations to reduce variables. Then, laboratory tests will characterize biochar's mechanical strength, permeability, pore structure, geochemical reactions with formation water, gas absorption, and so on. Field tests with long-term monitoring will follow to plug actual wells using unfracking. In this phase, we will evaluate biochar's performance in plug integrity, sealing, and toxic gas absorption. Once scientists and an advisory team determine best practices of plugging based on the feasibility study, a program to implement unfracking nationally can be created. After testing, unfracking can become the method of choice for plugging orphaned wells across the nation. Once made into policy, unfracking will create jobs and appeal to industry, state governments, taxpayers, and environmentalists. Using unfracking technology, we can realize a significant climate solution by cleaning up these orphan wells in a better way that also sequesters carbon. Climate scientists say we have about 7 years to implement solutions. Unfracking is one that can be fast-tracked to start right away. We would like to explore ways to work with the DOE to make this positive solution happen and happen soon.
All right. Let me stop sharing my screen and my hilarious desktop there. That's great. That's a real amazing, very, very clear overview of the solution and why it's needed. So what I'd like to do actually is I think it's important to dig into some of the technical aspects of what you lay out in summary. And that's why we have Dr. Lee here. And I kind of want to break those down. But maybe before I do that, real quickly, I do want to mention one thing is that in Colorado itself and now nationally at the federal level, there are a lot of resources that are being channeled to plug wells in conventional ways. So there is sort of a time element to this to try to really promote this method before that money all goes out the door and the plugging starts to happen. So there's some urgency to it. But Janice, is there anything you wanted to add before we talk about some of those technical questions, just in reference to the presentation itself, or anything you want to stress?
There's one thing I wanted to say. We made this video before the bill in Colorado started to go through the process. And I just want to make sure that everybody understands that the bill in Colorado is for a study. It's for a study to look at biochar in plugging orphan wells of, oil and gas orphan wells. And it's going to take a whole year to do the desk and lab part. And then we're going to have to do another piece of legislation in order to get permission to do the field part. So it's going to move kind of slowly. And that's one of the reasons why we're looking to expand this into other states and even other countries, because the more people working on it simultaneously and possibly sharing information, that's a really good thing. But we're making real headway. So if you live in a state that has a lot of fracking wells, and you know that they're going to be orphans and you know they're going to be leaking, 25% of all wells plugged with Portland cement are leaking. So that's a lot of methane and everything else in the air.
Great.
I'll stop now. We can get into more.
I'm glad you stressed that. So Dr. Lee, let's dig into a couple things. And well plugging is a need. And one of the things that was laid out in the video there is using biochar as an amendment. And I should say biochar, I think, is probably one of the most studied forms of at least CDR in terms of peer-reviewed academic literature. So there's a lot more we need to know, but it's quite well characterized. But the idea of adding biochar, ground up biochar, as a substitute or a mix for cement displaces some of the cement, but makes it stronger. So I was wondering if you could tell us what we know from an engineering perspective about biochar's use in this application. And if you could also talk about what was referenced in that video that we just showed, that there's a high rate of failure of conventional cement plugs. They crack a lot because of that fugitive gassing. And we think that there's a benefit for biochar to actually mitigate against that. So tell us what we know about biochar as an amendment for cement.
Sure. So biochar as a cement additive or concrete additive has been the idea around for a long time. The thing with Portland cement is it's a really carbon heavy material. It has a huge carbon footprint when producing it. So scientists around the world are trying to find ways to reduce this carbon footprint. One of the ways is to add biochar into it so that it on itself carries some of the carbon. But they also find out that it could just work like fly ash. Fly ash used to be a concrete additive, and it has been widely used in constructions, buildings, and so on. And biochar could just act like a additive, like fly ash, and mixed in the concrete with, and it does not affect the strength of the concrete, and as an additive, it stores carbon. So that has been the motivation of putting biochar in concrete. Now, in terms of orphan wells leaking, like in our field, Wiseman once said, all the concrete has fractures unless told otherwise, which means whenever you have a concrete structure, either it's a well plug or a casing, there's always going to be fractures in it. It could appear just as microfractures that does not interconnect for leakage, or it could just interconnect and start leaking. That's why Janice just mentioned that most of the wells will leak, more or less. So biochar, the additive in it, it has a lot of surface area that is able to absorb primarily big molecules such as the benzene and so on. So that's another advantage of adding biochar in cement.
Great, excellent. Yeah, and maybe also, Janice, if you could weigh in, there's another researcher who you've been connected with. I know you brought him actually to a meeting with the agency in Colorado at the University of Singapore, who's done extensive testing on this in a lab and I think even in a field setting. So I didn't know if you had anything to summarize just on a very specific researcher's work.
Well, that's Dr. Han Wai out of University of Singapore. And he, has written papers on this, but I don't have them at hand right now. I did post a link in the chat to a paper that I think is very, very good about the use of biochar in cement. And the conclusion there is that even 2% of biochar by weight in Portland cement will lower the carbon footprint significantly. And so, and also build strength and flexibility. So right there, we have a lot of the answer at only 2%. And we know that 2% of biochar is going to work in cement because we've seen it go into wells, in a fashion that is not data driven, but just practicing sort of proof of concept kind of thing. But, that's all very good news. And in Colorado, at least, that study will look into how much percentage can we add to the cement to make it strong and flexible, sequester the carbon. What is the correct amount? That's one of the big questions that needs to get answered.
Yes.
Dr. Lee, do you have more to add to that? Because that's a layperson's idea about it all.
No, I think you answered perfectly.
Great. And so, Janice, one thing I'm seeing people are saying that the link that you sent, it didn't look like it was a link. So just the fact sheet, if you have that as a hyperlink, please put that in there. And one thing I'll tell folks, when you receive the video tomorrow that you've RSVP'd, the video itself, I'm going to add some links in the show notes to that, the video notes, for some of the articles, the peer-reviewed articles around some of the things that we're talking about, if people really want to dive into the science and engineering of it. So you'll have access to that. Just a couple of other points that you brought up. If we could talk a little bit about, methane is the real problem from a climate perspective that's coming out of here. I think I heard once, and again, I can't give you a citation for it, might have been EDF, but I think there's more methane produced from orphan wells, they think, in terms of the strength of the greenhouse gas than cars on the road, I heard once. So I'll see if I can find a source for that as well. But what do we know? And again, I've looked at some of the peer-reviewed articles on this about the relationship between biochar and methane absorption. You alluded to it a bit in the video, but Dr. Lee, I don't know if there's anything else that you know and that you could share a little bit about that. Oh, sorry, that was for you, Dr. Lee.
Oh, okay. Sure. So the methane and biochar, I think it does absorb a little bit. If you think of methane emission in coal mines and so on, they do exist in those materials, but in terms of how much it will absorb, I don't have a number in my head right now, so I couldn't say much. But yeah, so methane is not the primary concern here because it's not really toxic. And if you think of the most effective way to mitigate climate change, that will primarily still be CO2. So that's why we're targeting in this direction.
Yeah, and I do think that certainly methane is just to be clear, is a very powerful greenhouse gas, and it's one that's very difficult to mitigate. And this is a point source of it. And so what we're proposing here, we know that there are properties of biochar that do absorb methane. Again, I can share two of the articles in the show notes. In your studies, and you're talking to researchers, Janice, I didn't know if you had anything you wanted to add to that.
Yeah, I do. In 2020, Reuters did an investigation and found that the US emitted 281,000 tons of methane in 2018. So that was 5 years ago. And if we're doing that per year, you know, that just gives you an idea of how much methane is going into the air. And, you know, while methane itself may not be considered the problem, it's linked to all these other chemicals. So the CO2 and the methane and the benzene and the toluene and the xylene and the heavy metals, those things are all a package that come out of fracking wells. The industry has focused, and so is the press, on methane, and that's the way they track how much is coming out of a well. So that's why we always talk about methane, because that's what's, excuse me, that's what's being tracked. But it's all these chemicals that come in the package that are also important. So I just wanted to stress that.
Great. And let's do this because I do want to get to the bill and I do want to get to some of the excellent questions, which some might be answered in the course of us talking about it. But I do want to, the actual matter of CDR, Dr. Lee, the carbon dioxide removal, there's a figure in Janice's video where she cites you where it's a pretty substantial range, but a potentially really significant amount of biochar that can actually be fit within that well. I'm wondering, can you just tell us a little bit about where that estimate came from, the amount of biochar that could fit within wells?
Yeah, so each well will have a volume to house the biochar. So that's the primary volume we're targeting to fill up, and then now the rest of the calculation all depends on the packing density we're going to use to put the biochar in it. For now, we're still in the process of figuring out how we are going to put the biochar in it. Is it in a fluid state or in a flying like powder state? So that will determine the packing density of biochar in these wells, and then we, in addition to that, there is the added biochar in the casing and the plugs. So all these added together is the mass of biochar we can potentially store on the ground, and then we convert that to immediate CO2, and that's the number we come up with.
Great, excellent. And if we could do this, Janice already did cover actually with the bill. The bill is a study bill. We want to base this and actually study. We're not proposing going out and just throwing biochar into orphan wells. We want to make sure that it works based on what we're hypothesizing here. Could you give us some insight, Wei, into what a test like that would look like? You've talked to us about that in detail. There's a lab portion, field portion, compressive strength. Tell us a little bit about what kind of study needs to be done to determine this.
Yeah, so there are two parts. One is biochar in the cement, and the other part is biochar as the filling material into the whole well. So on the cement part, we want to find how much the cement can house all these biochars, and does it affect the strength of the cement, either increasing or decreasing it. And also at the same time, does it increase the cement's ability to absorb the biochar? Does it reduce the fractures in the cement? So all these will be running in a standard cement or concrete test program. There's the 7-day strength, 28-day strength, and so on to test out a recipe to create this cement. So that's on the cement part. And on the biochar itself, we want to figure out how much surface area is there in the biochar we get, and then we want to put the biochar in the stress condition it's going to experience on the ground, right? On the ground, the biochar will experience a vertical stress, a horizontal stress, and it's packed really tight. And we want to figure out, does this affect the surface area in the biochar? Does this affect the ability of biochar to absorb these toxic gases? So in addition to that, we want to see if this biochar, the ability to absorb gases, will be affected by the formation water in when we put it in the wells. So this will be a set of characterizations such as a specific surface area, permeability tests, and triaxial tests for permeability under high pressure, high geostatic pressures, and so on. So this is another set of lab tests we need to do. If all this works out, we can move to the next phase, which is the field study. We use our knowledge we got from the lab tests, and then have a pilot test in the fields, and then monitor a lot of stuff during this process for like a long-term monitoring to see if the cement and the biochar is really behaving the way we want it to be. We can monitor the gas emission at the surface of the pilot well, and also we can monitor the water content, the seismic events when putting these in, and so on. So we're looking at about 1 or 2 years of study to really make this a convincing idea to put into practice.
It's great. And there's one other thing I think we should definitely speak to, particularly with an open air interest, is what's really interesting is about putting the biochar there has the benefits that we've talked about from a carbon removal perspective. One of the things that you would test for and have methods to test for is how does that elongate the durability or permanence of biochar by storing it in an enclosed environment. So I'm wondering, could you tell us a little bit about how is that simulated in a lab setting to know how it affects the biochar and how long it will last? Yeah,
so for like geomechanical testing, this is pretty standard, right? You apply the forces, the stress conditions, at certain depths, and also the temperature, the humidity, the water content, and so on. So we can all put all these parameters into our test machine, and then and at the same time monitor its behavior. Either it's creeping, or when it gets in contact with water, does it expand? And then we can do long-term tests to see how it behaves at these conditions. And after these tests, we can even take these out, which could never be possible in a field experiment. We can take these out and do very careful characterizations of these materials and see if it does absorb any of the gases we injected, if the pore structure has changed, or so on.
Yeah, so that's a good segue into some of the questions, because you've started to touch upon a lot of these really great technical questions. We were going to have a third guest on as a sort of a biochar expert, but unfortunately that was not made possible in the end. So some of the questions that are very particular about biochar, would be happy to send some links about some other biochar videos we've done in the past. But a couple of the questions that we have here, Ian asks a really good one. He appreciates the use of biochar for well plugging, but there's a more fundamental problem of who cares about them and who's going to pay for it. And we know that there is federal money. It's ultimately something that we hope there is a polluter pay, but there has to be money that is applied for this. But one of the things I think is really interesting is if with the carbon removal component of it, and particularly if it's high performing carbon removal, if it's enhanced in this way, then there are revenues that can be gained from the carbon markets, from carbon removal, which could actually help incentivize or offset some of the actual costs for this, which I think is exciting. So that was Ian's question. I don't know if this group here has this, but I know it's going to be part of the study, is what kind of biochars work? We're really interested in local biochar sources, which one would be best? But Tom asks a question, can you please characterize suitable biochar for this application? I heard 800C pyrolysis, 80 to 90% fixed carbon. What about feedstock, moisture content, ash content, and particle size? Again, we want to find that out through this study, but I don't know if anyone has anything more intelligent than I could say about it to offer to Tom's question. No, sorry, Tom. But again, we'll let you know when the study tells us, pending the passage of the bill. Let's see here. Again, some of these are highly biochar specific. Is most of your biochar production in retort units to capture the bio-oil fuels, biofuels, and the waste in some way versus open burn that release half of the carbon back to the atmosphere. One thing I will say about this as part of the scope of the study is what's the overall life cycle analysis. So we don't want to be using biochar where the net benefit of it is highly outweighed by emissions that might be caused in the process. So again, not to punt too much to the future, but that is why we're requesting this bill. Again, Janice, I don't know if you had anything to offer on that technical question, but
yeah, I did. And then I got distracted with the chat. Tell me again what that was about.
Yeah, so the question was, is most of your biochar production in retort units to capture the bio-oil biofuels and the waste in some way versus open burn that releases half of the carbon back? Yeah.
Yeah, I wanted to comment on the open burn thing. Biochar manufacturers who have state-of-the-art pyrolysis kilns are able to do this with little to no oxygen in the atmosphere of the kiln and little to no release of carbon dioxide into the air. There are people in the world who make biochar in a barrel in their backyard, and that is not what we're talking about here. I mean, those applications are interesting and fun and, kind of on a gardening basis and stuff like that. But what we're talking about is proposing that biochar be made in a state-of-the-art way so that it's really clean and there's no CO2 going into the air.
Yeah. And I want to say that it is really impressive for something that seems so quote unquote nature-based, the level of innovation that is going in to biochar, including modular biochar development, where you can bring the kilns close to the site, which could be important for an application like this because these are many different little locations. I know that Toby Bryce, our OpenAir member and host of This is CDR, is on. Toby, if you happen to have it at your hand, feel free to throw some of the other OpenAir This is CDR videos about biochar into the chat if you can. We also have a question from Guy here. This is a good one, probably for Dr. Lee. Is there a limit to biochar accumulation capacity of fugitive emissions? Assuming the wells leak indefinitely, is there a limit to how much the biochar can absorb? That's a great question.
Well, for a definitive answer, I would still say we have to study that. But here's an analogous answer for that, right? So for the biochar we get our hands on normal conditions, for example, active carbon, as small as it is, the surface area in it is enormous. Yes. And for usually gas absorption, you can just imagine one gas molecule covering that surface, like one layer of gas molecule covering that surface. That is a lot of gas molecules we're talking about. So I do see great potential of this material in absorbing gas, but for the definitive answer, I think we still need to study that. We do have the device in our lab to study for that. That's the specific gravity. So the surface area over the mass of the material. So you can expect a large area for this type of material. Great.
Excellent. And Phil asked a good question. What's the potential value of biochar in this application, presumably from a carbon removal credit perspective? We don't know, but you can look, like, for instance, at puro.earth, the averages of what is, sort of fetched for a ton. It's, usually around 150, but some of them can be much larger. But again, if we find that there's evidence that in this type of environment, it prolongs it, that would equate to actually higher value credits. So that's a really exciting thing that we've already had some early discussions with some of the certifiers for that. This is a great question too. And I don't know if we have an answer for it, but it's one we have been thinking about. This is from Guy as well. Do you know if anyone has looked into the application of biochar to plug and remediate fugitive emissions from old mines? I don't know if anybody knows that.
People bring this up all the time. And it's not something I've looked into exactly, but I imagine that this will only help that along, because some of the research will apply. And Dr. Lee nodding his head because, yeah, it's only going to help that effort.
Yeah, mining has been a big issue around the world. It's dangerous and it has a lot of pollutions. And even after the mine is abandoned, it emits gases, it creates sinkholes and hazards, all kinds of things. So if, like, for a wild idea, we put this biochar and we use it as the concrete to reinforce and seal those mines, the walls of the cracks of the mines, maybe this could be a solution for the mining industry too.
Yeah, and I know there are companies too, which there is a biochar component to it, but it's mostly bio oil production that takes waste materials and creates a viscous bio oil. Charm Industrial, who we've had on This Is CDR before, very exciting company. Now with a footprint in Colorado, they're looking very broadly across many different types of depleted or retired or orphaned infrastructure, including mines as well. So there's different ways to achieve that potentially. So this is a good question too, from Dan. Can already plugged wells be converted into plugging with biochar? I have a thought on that, but I'm not qualified as Dr. Lee. Dr. Lee, what do you think of that?
Well, this is a tough one because you don't know what's in those already sealed wells. You could be opening a Pandora's box and you don't know that. But if it's necessary, I don't see why not, right? If you have the proper equipment to see, it's safe to open part of the well and then put the biochar in it and seal it again. Why not?
Yeah.
Yeah, can I weigh in on that too, Chris?
Go for it.
Well, since 25% of wells plugged just with Portland cement are going to fail, those need to be replugged anyway. And in the replugging, that's when we could use biochar in the application most inexpensively because they need to be replugged anyway. And since it's going to make it last longer and do better, it becomes really cost effective to do it that way. And I'm pretty sure that the oil and gas industry is thinking about that as they're thinking about the decades ahead, because as we phase out of fossil fuels, we're going to have more and more of these wells that are going to be abandoned, hopefully not abandoned, but are going to need to be plugged. And this is going to be a period in our history where we're going to have to plug these wells and hopefully plug them with biochar. And then when we're done with fossil fuel, this will be something that will be something in our past. This is a period of time that we're going into with this kind of a remediation. My guess is like it's going to be 2 or 3 decades of doing this. And then we will be off of fossil fuels, hopefully, and we won't need to do it anymore. So it's kind of interesting to think of it as something that is the beginning of the phase out, the beginning of the transition, and therefore a really positive step.
Yeah, absolutely. I just want to give some feedback here. Nisha, who's one of our most regular viewers of This Is CDR. Hey, Nisha, how you doing? Yes, are we applying for an X Prize, which I think is high praise in and of itself as a question. But we are definitely going to be seeking pretty opportunistically funding to do research. What the state of Colorado will be able to do if this bill passes is one thing. Some of these are going to be highly locally specific. So we really do have a federal audience in mind. And so for those of you, as I'll talk about a call to action in a minute, we want to do this in multiple states, but we want the federal government's attention. Janice was able to actually give this very presentation to some folks within the DOE. We feel like there's conceptual interest in a lot of high places. And so part of our advocacy will certainly be focused on that. But we will also, if anybody knows of any other grantors or foundations that might be interested, as well as, I should point out, Janice has done all of this entirely as a volunteer as well. And I think for all the work she's done, we're trying to get her into a position where she might get compensated so she could be even more effective. So if people have any ideas on that, please put it in the chat. So I think we covered most of the questions directly or indirectly. Martin, you asked a question about higher porosity surface area. I think Dr. Lee did address that. And now let's turn to Carl's question, which is a good segue into the call of action. And he says, this is Carl Dans, one of the most prominent of OpenAir members. He said, You said once made into policy, please say more about the specific needs. So presumably what kind of activism is required. Definitely calling your legislators about the bill and asking them to support it and provide the video. It's only 10 minutes long and it's highly accessible. So anybody in the state of Colorado, please do share it with your legislator and tell them that you support the bill. And if you're in another state, when you receive this video or just use Janice's video, it's probably more accessible for a legislator. Say, hey, we want to have a study in our state. We want to look at what Colorado is doing. And Janice, I don't know if you want to say anything more about what we're trying to do here. What are our advocacy ambitions here for Unfracking?
Well, I think you said it all pretty well, Chris. More states, more interest. And to answer somebody's question earlier about feedstocks from other places other than Colorado, that yes, in fact, all over the United States and the world, there are feedstocks. So it doesn't need to be the same kind of feedstock we have in Colorado, which is dead trees. In other places, it could be pecan shells, it could be rice husks, it could be corn stalks. There are all kinds of woody biomass feedstocks out there. And so to some extent, it will be tailored to the local economy and the local feedstock supply. So any state will have something that can be pyrolyzed and turned into biochar.
Great. And so with that, I want to say, I just put a link there. If you're already an OpenAir member and you're in our Discord, you know where to find me. You can ping me. Me and Janice have been meeting up once a week to get ready to this point. And now we want to recruit more people to join our team. That's what we do at OpenAir. We form usually relatively small groups of people. And we get things done. And so wherever you are across the country or wherever you are, if this is of interest to you, please join us and let's get this thing done in Colorado and elsewhere. And I'm trying to think if there's anything else I needed to add to that. Yeah, so you can find that in the link that I just shared, openair.collective.cc/join. And we're going to get going. So anything else that we want to have as a final thought? We're at time. I thought this was excellent. I want to thank both Janice for her just extraordinary Herculean visionary work on this, and for Dr. Lee coming in and answering all of mine and Janice's dumb basic questions about how engineering works. So we have a solid core going, but please do join us. And I want to thank everybody for joining this webinar, but please do join us in this effort. So I'm going to go ahead and keep the Zoom on just for a few minutes. If people want to copy any links, I'll be sending out the video hopefully by tomorrow morning, maybe Saturday, which will include a lot of relevant links in it as well. And hope to hear from some of you soon. Thanks, Janice. Thanks, Lee. And thanks, everyone.
Thank you.